Hello, everyone, welcome back to my channel, The Resting Mind. In the silent depths of the constellation, Scutum, 8 billion years ago, a fire was lit that should have lasted seconds, but instead, it refused to go out. Imagine a flash of light so intense that it outshines every star in its galaxy combined. A scream of energy from the very edge of the observable universe that carries the news of a catastrophic death. Usually, these events, which we call gamma-ray bursts, are the ultimate cosmic blink and you miss it moments. They are the fleeting signatures of a star collapsing into a black hole, a process that is violent, definitive, and mercifully brief. But on July 2nd, 2025, the Fermi Gamma Ray Space Telescope watched as the rules of physics seemed to bend. An alert triggered, signaling the arrival of GRB 250702b, and then something impossible happened. The signal didn't fade. It didn't stutter and die. It held its breath for 7 hours, shattering every record we had ever recorded for the duration of a cosmic explosion. Tonight, we journey 8 billion light-years away to a place where a black hole, only 11 miles wide, staged a 7-hour feast that has left the scientific community in a state of profound awe. This is the story of the 7-hour flash, a record-breaking cataclysm that forced us to look at the James Webb Space Telescope, not just as a camera for the past, but as a forensic tool for a crime scene of unimaginable proportions. To understand the gravity of what was found, we have to recognize that in the vastness of the cosmos, we find a strange kind of peace in the predictable. We expect stars to die in certain ways. We expect the laws of thermodynamics to govern the pace of a collapse. But GRB 250702b was a defiance of that peace. It was a fire that burned with the energy of 2.2 times 10 to the 54th ergs, placing it among the 20 most energetic events ever witnessed in the history of human astronomy. As you settle in, perhaps adjusting your own perspective to the slow, rhythmic pulse of the universe, consider the scale of what we are discussing. 8 billion years ago, the Earth did not exist. Our sun was not even a pocket of dust in a nebula. Yet, this light was already traveling through the freezing, silent corridors of the intergalactic void, carrying a secret that would eventually reach the gold-plated mirrors of the JWST. The mystery began with a ghost signal, a strange rhythmic X-ray emission detected by the Einstein probe a full 24 hours before the main explosion even occurred. It was as if the universe was offering a warning, a pre-dawn shadow of the total destruction to come. We often feel that the universe is stable or static, but in this very moment, we are learning that the collapsar model, the textbook explanation for how massive stars die, may be incomplete. To comprehend the sheer magnitude of this event, we must leave the familiar setting of our solar system behind and adjust our eyes to a light that has been traveling for more than half the age of time itself. We are looking at a host galaxy that is twice the mass of our own Milky Way, a giant hidden behind a thick, suffocating wall of cosmic dust. For years, this galaxy appeared to us as a blurred smudge, perhaps two smaller galaxies in the middle of a slow-motion car crash. But when the James Webb Space Telescope turned its infrared gaze towards Scutum, the dust became transparent, revealing a single, massive powerhouse of a galaxy that had been nursing a monster in its core. Within that dust-choked environment, a micro-TDE, or a tidal disruption event, was taking place. This wasn't just a star dying, It was a black hole merging with a companion star, a stripped helium sun that was literally consumed from the inside out. The distance that breaks our brains is often hard to bridge, but think of it this way. If the sun were the size of a white blood cell, the distance to this burst would span the entire continent. Yet, the black hole at the center of this drama is tiny by comparison. Only about 3 times the mass of our sun, with an event horizon no wider than a small city. How could something so small create a disturbance so large that it could be seen across half the universe for 7 hours straight? That is the question that sent shockwaves through the international astronomical community. It was a scientific crisis that turned into a global relay race as telescopes from the Fermi satellite to the Very Large Array in New Mexico scrambled to catch the afterglow before it vanished into the eternal dark. As we delve deeper into this mystery, we find ourselves in the role of the cosmic detective, sifting through the spectral data to find the chemical signatures of a stellar feast. The JWST provided the definitive evidence, showing us that this wasn't the standard death of a single star, but a rare, complex dance between 2 celestial bodies. It is a fascinating reminder that physics doesn't know everything yet. There are still chapters of the cosmic story that are being written in the high-energy flashes of distant constellations. You are a data point in this collective exploration tonight, a witness to a discovery that challenges our understanding of how gravity's heavy hand shapes the life cycle of the stars. In the vastness of the cosmos, there is a strange kind of beauty in realizing that even the most distant, ancient fires can still teach us something new about the world we inhabit today. The light we are analyzing tonight is an old light, a patient light. It has survived the expansion of space and the passage of eons just to arrive here, touching the sensors of our most advanced machines. It tells us of a black hole that refused to eat quickly, choosing instead to savor its companion over the course of hours, creating a luminous shroud of ionized gas that glows with the ghostly hues of a reality we are only beginning to map. This is the 7-hour flash, a record-breaking anomaly that reminds us that the universe is never truly silent. It is always speaking, always whispering its secrets through the medium of light and shadow, waiting for us to find the right way to listen. As we prepare to look closer at the warning signal and the dust-filled halls of that massive host galaxy, let the scale of this event settle over you like a blanket. We are small, yes, but we are the ones who have learned to see the fire 8 billion years after it was lit. In this nightly ritual of learning and discovery, we find that the most terrifying distances are also the most beautiful, and the silence of the void is actually filled with the echoes of 1,000 different ways for a star to say goodbye. Before the sky tore open, before the instruments on the Fermi Gamma Ray Space Telescope began their frantic 7-hour dance with the light of 8 billion years ago, there was a whisper. It was a signal so faint and so early that, under normal circumstances, it might have been dismissed as cosmic background noise or a momentary glitch in the vast silicon mind of our orbital monitors. We call this a ghost signal. In the sterile, high-altitude silence of the Einstein probe, a dedicated X-ray eyes in the sky, a strange pulse was recorded a full 24 hours before the main explosion of GRB 250702b. This was the cosmic equivalent of a shadow appearing before the object that casts it, a pre-flash, a low-energy warning that the fabric of space was about to be shredded by an event of record-breaking magnitude. Imagine a star that has lived for millions of years, a stable nuclear furnace in the heart of a galaxy twice as massive as our own Milky Way. This star was not alone. It was locked in a gravitational embrace with a companion, a silent sentinel that had already collapsed into a stellar mass black hole. This black hole, a dark sphere perhaps only 11 miles wide, carried the weight of 3 suns within its tiny, impenetrable horizon. As they spiraled closer, the black hole did not simply wait for the star to die, it began to feed. The ghost signal we detected was the heat of that first bite, the agonizing friction of stellar gas being ripped away and accelerated to near-light speeds as it spiraled into the abyss. It was a micro-TDE, a tidal disruption event, on a scale so intimate and yet so violent that it sent X-rays screaming across the void a day before the final, catastrophic merger. This precursor activity challenges everything we thought we knew about the timeline of a star's demise. Usually, we expect the grand finale to be a sudden, singular collapse, the collapsar model, where a giant star folds in on itself in an instant. But GRB 250702b was telling a different story. It was a slow-motion car crash on a galactic scale, a feast that lasted for hours and hours, because the meal was being consumed from the inside out. The ghost signal was the sound of the door creaking open. It was the first evidence that this was not a standard stellar death, but a rare, prolonged cannibalism. By the time the primary gamma-ray flash arrived, the black hole had already been gorging for 24 hours, building up a reservoir of energy that would eventually shatter every record in our digital archives. We are only now beginning to realize that the universe often whispers before it screams, and if we are patient enough to listen to the silence, we might just catch the ghost before the fire begins. When the James Webb Space Telescope finally swiveled its golden hexagonal mirrors toward the coordinates in the constellation Scutum, astronomers expected to see the cooling embers of a shattered star. Instead, the data flowing back to Earth revealed something far more enigmatic, a dense, impenetrable wall of cosmic dust that seemed to swallow the light of the explosion whole. In the infrared spectrum, where Webb excels, the scene appeared as a vast field of deep amber, a thick fog of silicates and carbon soot that had been drifting through this distant galaxy for eons. It was as if the universe had intentionally drawn a curtain over the crime scene, forcing us to peer through a haze that would have blinded any other instrument in human history. Nestled within this golden shroud was a single pinpoint flicker of violet-white light, a sharp contrast to the warm, earthy tones of the surrounding gas. This tiny spark didn't behave like a fading afterglow. It pulsed slowly and rhythmically, like a steady heartbeat echoing from the center of a storm. Scientists soon realized they were looking at a galaxy twice as massive as our own Milky Way, a true titan of the early universe located 8 billion light-years away. For years, ground-based telescopes had misinterpreted this region, suspecting 2 galaxies were in the process of merging. But Webb's superior resolution clarified the truth. This was a single, monstrous entity, so choked with the debris of past stellar generations that it had become a cosmic furnace, hiding its most violent secrets behind a veil of soot. The presence of this dust wall changes everything we thought we knew about how these massive bursts are born. Normally, we expect a gamma-ray burst to occur in a relatively clean environment where the jet of energy can pierce through space unimpeded. But here, the black hole was born inside a literal cloud of ash, the remnants of a stripped helium star that had been systematically dismantled by its companion. As the black hole gorged on this material, it didn't just emit light, it cooked the surrounding environment, heating the dust until it glowed with a ghostly infrared fever. We are beginning to see how the sausage is made in the most extreme laboratories of the cosmos, realizing that the most powerful flashes in the universe often begin in the dark, cramped quarters of a stellar nursery turned graveyard. This discovery forces us to confront a new kind of scientific humility, recognizing that our standard models of stellar death are still just making steam when compared to the reality of the deep sky. The amber light we see today is a bridge to a time when the universe was still in its turbulent youth, a period of rapid construction and even more rapid destruction. To look into this wall of dust is to realize that space is never truly empty. It is a crowded, messy, and beautiful tapestry of recycled star stuff. We are all just data points in this collective exploration, watching a violet heartbeat pulse behind a golden screen, waiting for the dust to settle so we can finally see the face of the monster that created it. The digital world of astrophysics usually breathes in a steady, rhythmic pulse of automated data, a silent conversation between orbiting sensors and the silicon brains waiting on the ground. On the night of July 2nd, 2025, that conversation was interrupted by a scream from the constellation Scutum. The Fermi Gamma Ray Space Telescope, a silent sentinel orbiting far above our atmosphere, registered a sudden, sharp spike in high-energy radiation. It was an event labeled GRB 250702b, and at first, it looked like just another data point in the collective history of stellar death. In the initial seconds, the automated alert system did what it was designed to do. It calculated a rough position, sent a burst of coordinates to a global network of telescopes, and prepared to move on to the next patch of darkness. We often think of these cosmic explosions as fleeting, momentary flashes that define the brevity of space. Yet this particular monster didn't know how to die. To understand the crisis that was about to unfold, we have to look at the standard clockwork of the universe. Most long-duration gamma-ray bursts are finished in a matter of seconds, perhaps a few minutes if the dying star is particularly massive. They are the final desperate gasps of a collapsing sun, a process of nuclear synthesis, reaching its violent logical conclusion. But as the clock in the operations center passed the 10-minute mark, the Fermi data showed no sign of tapering off. The energy was not just lingering, it was pouring into the vacuum with a consistency that defied every model we have for how a star collapses. By the 1-hour mark, the routine detection had transformed into a scientific anomaly that threatened to break our brains. Astronomers across the globe, woken by the persistent chiming of their mobile devices, watched their screens in a state of comfortable terror as the light curve remained stubbornly flat and high. The standard model of a collapser, a star falling in on itself to birth a black hole, simply cannot sustain a relativistic jet for this amount of time. It is a matter of fuel and physics. A star only has so much mass to feed the engine. Yet GRB 250702b continued to roar for 2 hours, then 4, eventually shattering the 7-hour barrier. This was nearly double the previous record held by any known burst, a duration that suggests the engine at the heart of this explosion was being fed by something far more substantial than a single dying star. As the midnight crisis deepened, a global mobilization began. The Einstein probe and the Gemini North telescope were swung into position, their massive mirrors catching the afterglow of a fire that refused to go out. We were witnessing a cosmic joke played by gravity, a spectacle that forced us to realize that physics doesn't know everything yet. There is a strange kind of peace in watching the impossible happen in real time, even if that impossibility is occurring 8 billion light years away. For 7 hours, this single point in space released at least 2.2 times 10 to the 54th ergs of energy, a number so large it effectively loses all meaning to the human mind. It was as if the universe had decided to pull back the kilt of the standard model to reveal a mechanism we had never dared to imagine. Scientists sat in darkened rooms, the scrolling green text of terminal data reflecting off their faces like a digital ghost, trying to comprehend a jet that could stay active for nearly a third of a day. But as the gamma rays finally began to dim, a new mystery was rising from the data of the day before, suggesting that this monster had sent a warning long before it finally arrived in our light cone. As the astronomers began to backtrack through the digital archives, scouring the hours leading up to that impossible 7-hour flash, they stumbled upon a ghost in the machine. While the gamma ray burst itself was a roar that shook the foundations of high-energy physics, the silence that preceded it was not truly silent. Tucked away in the telemetry of the Einstein probe was a sequence of soft, rhythmic pulses, a series of X-ray emissions that had begun a full 24 hours before the main event. The universe gave us a 24-hour warning, a silent X-ray scream before the literal sky fell. This was the precursor shadow, a warning shot fired from the deep past that suggests the final explosion was not a sudden snapping of cosmic fingers, but a slow, agonizing descent into the abyss. To understand the physics of this precursor is to witness a star being flayed alive. In the standard model of a collapsing star, the transition from life to a black hole is near instantaneous. But here, something was stripping the star's outer layers, peeling back the stellar envelope, and casting it into the surrounding void an entire day before the core finally surrendered. It is a process that defies our simpler maps of stellar death. We are looking at a celestial body leaking its life force, bleeding high-energy radiation as its companion, a compact, invisible predator slowly spiraled inward, nibbling at the edges of its host before the final, violent plunge. When we speak of where this happened, we must adjust our eyes to a scale that begins to break our brains. The light from GRB 250702b arrived at our sensors from a redshift of Z equals 1.036. In the language of the cosmos, this means the photons we captured tonight have been traveling for approximately 8 billion years. We are looking halfway across the observable universe, peering into an era when the Earth did not yet exist, and the Sun was nothing more than a swirl of cold dust in a nameless nebula. The sheer distance acts as a cosmic filter, yet the signal was so powerful it arrived with the clarity of a nearby neighbor. The energy calculation for this event is a number that feels more like poetry than mathematics. It released at least 2.2 times 10 to the 54th power ergs of energy. To find a terrestrial anchor for such a magnitude, consider our own Sun. It is a stable middle-aged star that has been burning for 5 billion years and will likely burn for 5 billion more. If you were to take every single photon the Sun will emit over its entire 10 billion year life, every spark of heat and light it will ever produce, and compress that energy into a single 7-hour window, you would still not reach the fury of this single burst. It is a level of power that turns solid matter into a plasma jet, moving at 99.9% the speed of light. And yet, we are left with a lingering, restless question that keeps researchers staring at their screens in the small hours of the morning. What kind of object can leak energy for a full day, flickering in the X-ray spectrum like a dying candle, before finally erupting into the most durable explosion ever recorded? It suggests a mechanism we have never seen in the wild. A stellar feast that lasted far longer than the laws of physics usually allow. To find the culprit, we needed eyes that could see through the very fabric of cosmic smoke. What lives in the gap between the warning and the blow? As the data began to clarify, it became apparent that this monster was not standing in an open field of empty space. It was hiding, wrapped in a shroud so thick that ordinary light could never hope to escape. To see the face of the killer, we would have to look past the visible, into the long wavelength infrared, where the secrets of the dust are kept. The James Webb Space Telescope does not look at the universe the way our eyes do. It breathes in the heat of the cosmos, capturing the faint infrared glow of objects hidden behind curtains of interstellar soot. To solve the mystery of the 7-hour flash, mission controllers pivoted the massive gold-plated mirrors of Webb toward a specific crowded patch of the constellation Scutum. In this region of the sky, the gas and dust are so dense they act like a physical barrier, a wall that had swallowed the visible light of the explosion before it could ever reach our terrestrial telescopes. As the first data packets began to stream back to Earth, the scientific community experienced a profound sense of cognitive vertigo. We had expected to find a small, frantic, star-forming dwarf galaxy, the typical breeding ground for such violent gamma-ray bursts. Instead, the infrared gaze of Webb pierced through the dust-choked regions to reveal a titan. Emerging from the darkness was a host galaxy of staggering proportions, a celestial behemoth twice the mass of our own Milky Way. This wasn't a fragile nursery for short-lived stars. It was an ancient, massive structural anchor in the deep universe. At first, the data was confusing, presenting a jagged, chaotic shape that led many researchers to believe they were witnessing a merger illusion. It appeared as though two distinct galaxies were in the middle of a violent collision, their gravitational fields tearing each other apart. However, as Webb's near-infrared spectrograph refined the image, the truth became even more unsettling. This was not two galaxies meeting, but one single, massive, and hideously distorted structure. The galaxy was bloated and warped, filled with the scars of past gravitational trauma. And it was within this high-pressure environment that the record-breaking burst had been forged. Webb didn't just see the fire. It saw the massive, dusty cathedral in which the fire was built. By analyzing the chemical signatures within that infrared light, the telescope performed a feat of cosmic forensic science. The spectroscopy revealed what astronomers call a heavy metal environment, a region of space saturated with elements heavier than hydrogen and helium. This discovery complicated everything we thought we knew about the birth of such massive bursts. Typically, the engines of these explosions require clean gas to function. Yet here was a monster thriving in a graveyard of metallic dust. When we revisit the 7-hour duration of the flash, the sheer mass of this host galaxy begins to provide a sense of scale that breaks our brains. The energy required to punch through such a dense metallic environment and remain visible for nearly a third of a day implies a power source of terrifying efficiency. We are no longer looking at a simple stellar collapse, but a sustained, agonizing release of energy that defies the standard models of physics. As we peel back the layers of this dusty giant, we find that the galaxy itself was merely the shell. Hidden within this dusty giant was a predator of impossible proportions. The predator we found lurking in the dust of that distant galaxy was not the supermassive heart of a quasar, nor was it a giant of the cosmic stage. Instead, it is something far more intimate and unsettling. Scientists call it a micro-TDE, a tidal disruption event occurring not between a galaxy and a star, but between two stellar siblings. At the center of this 7-hour flash was a black hole with a mass only 3 times that of our Sun. If you were to place this object on a map of Earth, its event horizon, the point of no return where light itself is trapped, would span only 11 miles. It is a dark, silent sphere smaller than a mid-sized city, yet it possesses a gravitational grip that can unmake a sun. This was a stellar feast, a slow-motion consumption, where the predator was smaller than a city, and the prey was a sun. The prey in this case was a stripped helium star, a massive orb that had already lost its outer layers of hydrogen, leaving its hot, dense core exposed. In a standard supernova, a star collapses and explodes in a matter of seconds, but GRB 250702b refused to follow the script. The black hole did not simply strike its companion. It entered the common envelope of the helium star, sinking into the stellar interior like a lead weight in an ocean of fire. This is the interior feast, a rare and chaotic process where the black hole begins to consume its host from the inside out. As the black hole spiraled deeper into the helium star, the calculation of chaos began. Normally, the material falling toward a black hole creates an accretion disk that vanishes quickly as the energy is spent. However, because the black hole was so small, it could only swallow so much material at once. This created a bottleneck of celestial proportions, what physicists sometimes call the infinity problem of duration. The accretion disk stayed stable and bright for 7 hours because the black hole was a delicate eater, meticulously stripping the star layer by layer rather than gulping it down in a single instant. This sustained the jet of gamma rays, pointing it directly at our corner of the universe for a third of a day. It was a masterpiece of gravitational efficiency, a sustained scream of light emerging from the belly of a dying sun. But even a feast this large leaves behind a ghost. As the primary furnace of the gamma ray burst finally began to exhaust its initial reservoir of fuel, the high-energy screaming of the universe transitioned into a profound, heavy silence. In the weeks following the flash, the universe went quiet, leaving us to sift through the cooling ashes of a record-breaking fire. This transition marks the birth of the afterglow, a ghostly remnant that carries the true history of the event, long after the violent prompt emission has vanished from our sensors. To capture this fading heartbeat, astronomers turned their attention away from the high-energy satellites and toward the high desert plains of New Mexico, where the 27 giant antennas of the Very Large Array stood like silent sentinels under the expansive American sky. Capturing a radio afterglow is an exercise in extreme patience and mechanical precision. While the initial burst of gamma rays traveled at nearly the speed of light, the surrounding material, the interstellar gas and dust choked within that distant galaxy, acted as a cosmic brake. This interaction creates a phenomenon where we are essentially allowed to watch the past in slow motion. Because the shockwave from the explosion must plow through the dense environment surrounding the black hole, the resulting light is shifted into lower frequencies, moving from the violent violet of X-rays into the calm, rhythmic pulses of radio waves. It is a fortunate barrier of physics. Without this natural deceleration, the most vital clues about the explosion's energy would pass us by in a heartbeat, lost to the void before we could even point our telescopes. The coordination required to track GRB 250702b across these different scales of light was nothing short of a global symphony. At Carnegie Mellon and other leading institutions, researchers lived in a state of synchronized exhaustion, bridging the gap between ground-based radio dishes and space-based infrared mirrors. They had to ensure that as the Einstein probe lost the signal in the X-ray spectrum, the Very Large Array was already tuned to the exact coordinates in the constellation Scutum. This wasn't merely a matter of moving a telescope. It involved processing petabytes of raw data in real time to filter out the noise of our own busy planet. They had to be certain that this 7-hour monster wasn't a fluke of the equipment or a localized glitch in the deep space network, but a genuine message from 8 billion years ago. As the numbers finally settled into the servers, the sheer scale of the event became undeniable. This burst had released at least 2.2 times 10 to the 54th power ergs of energy, a number so vast that it effectively breaks our brains if we try to compare it to anything terrestrial. To find a comparison, we must look at the top 20 most energetic events ever recorded since the dawn of time, placing this single star's death in the same conversation as the ripples of the Big Bang itself. It was a heavyweight champion of cosmic proportions, outshining entire clusters of galaxies for a brief, brilliant window of time. We were no longer just looking at a star that had died. We were looking at a fundamental shift in our understanding of how much power a single point in space can hold. As the numbers settled, the implications began to shake the foundations of astrophysics. To understand why this 7-hour flash remains such a profound disruption to our celestial maps, we must first look at the clockwork of a standard stellar death. In the traditional collapsar model, the death of a massive star is a frantic, violent affair that usually concludes its primary business in a matter of mere seconds. When a star 20 times the mass of our Sun exhausts its nuclear fuel, the outward pressure of fusion vanishes and gravity wins its long-standing war with light. The core collapses into a black hole almost instantly, and as the outer layers of the star fall inward, they are whipped into a swirling disk of plasma. Magnetic fields then funnel this material into two narrow, incredibly powerful jets that pierce through the star's shell and scream into the vacuum of space. In this established framework, the engine of the burst, the accretion of matter onto the new black hole, runs out of fuel quickly. Most gamma-ray bursts are over before a human observer could finish a single deep breath. Yet, as the data from GRB 250702b continued to stream into our terrestrial consoles, that standard model began to splinter and fail. An iron core collapse simply does not have the stamina for a 7-hour performance. It is a sprint, not a marathon, and the physics of a single collapsing star cannot account for a jet that remains active for nearly a third of a day. The energy requirements alone would demand a star of such impossible size that it would defy the laws of stellar evolution. We were witnessing a failure of theory, a moment where the chalkboard equations of the 20th century could no longer contain the reality of the 21st. Physics demanded the burst end in minutes. The universe simply refused to obey. The answer, we now believe, lay in the stripped nature of the victim. This wasn't a solitary star meeting its end in the lonely dark, but a binary system, a cosmic dance between a small black hole and a companion star made of nearly pure helium. This companion had already lost its outer hydrogen envelope, leaving behind a dense, exposed core of helium that changed the fluid dynamics of the entire explosion. As the black hole began to consume its partner, the helium didn't just fall in, it created a massive bloated reservoir of fuel. This brings us to the Schwarzschild barrier, a concept that describes the physical limits of a black hole's reach. Because the central black hole in this event was a micromonster, only about 3 times the mass of our Sun, its event horizon was incredibly small, perhaps only 11 miles across. This tiny diameter acted as a physical bottleneck. Even though there was a massive feast of helium available, the black hole could only swallow so much at once. It was like trying to drain a great lake through a drinking straw. The energy couldn't all be released in one catastrophic flash. Instead, it was forced into a slow, sustained burn that lasted for hours. This tiny event horizon, the very thing we thought would make the burst smaller, was actually the mechanism that made it last so long. If this can happen once, it suggests the graveyard of the universe is far more crowded than we thought. As the final echoes of that high-energy feast subsided at the source, the real journey began. A silent, patient trek across the grandest stage imaginable. The photons birthed in that 7-hour flash were cast out into a universe that looked very different from the one we inhabit today. 8 billion years ago, the cosmos was in its vibrant Middle Ages, a period of frantic activity known as the cosmic noon, when galaxies were forging stars at a rate nearly 10 times higher than what we see in our modern, quieter neighborhood. These gamma rays were the first messengers to leave that dusty, massive host galaxy, escaping the gravitational pull of a black hole that had just finished its meal. To understand the scale of this journey is to experience a form of cosmic vertigo. These particles of light did not merely travel through space, they drifted through the vast, shivering architecture of the cosmic web. They passed through the great voids, those immense, empty bubbles millions of light years across, where the density of matter is so low that a single atom might be the only inhabitant for miles. They skirted the edges of galactic filaments, those glowing ribbons of dark matter and gas where thousands of galaxies cluster like dew on a spider's web. For 8 billion years, while Earth was still a swirl of unformed dust and the sun had not yet ignited its nuclear fire, this light was a silent sentinel, crossing the ever-expanding gulfs of the deep. However, the space through which this light traveled was not a static background. It was a living, stretching fabric. As the photons moved, the very universe they inhabited grew larger, pulling at the wavelengths of the light itself. What began as high-frequency, energetic blue and violet radiation was slowly, relentlessly stretched out, shifting toward the longer, cooler red end of the spectrum. This cosmological redshift is the reason the James Webb Space Telescope was so vital for this discovery. By the time the signal reached our corner of the sky, it had been colored and softened by the expansion of the universe, carrying the signature of a world that has long since changed. We must also consider the dusty wall through which this signal first had to punch. The host galaxy of GRB 250702b was not a clean, transparent place. It was choked with the soot of 1,000 supernovae, a thick veil of carbon and silicate grains. While this dust could not stop the ferocity of the gamma rays, it acted as a cosmic filter, absorbing shorter wavelengths and re-radiating them as heat. This didn't hide the signal. Instead, it colored our understanding, providing a chemical fingerprint of the environment surrounding the explosion. It told us that this was a mature, massive galaxy, twice the size of our own Milky Way, thriving in a time when the universe was still raw and energetic. The most haunting realization of this travel is the weight of time itself. By the time we saw the flash, the black hole had likely evaporated, and the galaxy itself had drifted millions of light years away from the coordinates where the light first escaped. We are effectively looking at a posthumous signal, a ghost of an event that concluded eons before the first multicellular life appeared in our oceans. We are not just observing a distant explosion, we are witnesses to a history that no longer exists in the present tense. It is a reminder that in the vastness of the cosmos, we find a strange kind of peace, holding a light that has finally found its way home after a journey that breaks our brains. What remains is not just data, but a blueprint for the future of discovery. The detection of such a profound anomaly required more than just the sharpest eyes. It demanded a new kind of sentinel, one capable of watching the entire sky at once. This role was filled by the Einstein probe, a mission designed with wide-field X-ray vision inspired by the complex geometry of a lobster's eye. While older generations of telescopes were like peering through a narrow straw at a vast ocean, this new guardian could scan the horizon for the faint, flickering precursors of cosmic violence. It was this specific capability that allowed us to catch the whisper before the scream, identifying the strange X-ray activity that began a full 24 hours before the primary 7-hour flash. Without these wide-field eyes, the most critical clues to the star's internal struggle would have remained hidden in the dark, lost to the sheer scale of the celestial background. We have entered what researchers call the multi-messenger era, a time when we no longer rely on light alone to tell the story of the universe. To understand GRB 250702b, theorists had to weave together the invisible ripples of gravitational wave theory with the blinding brilliance of electromagnetic observation. It is a collaborative dance between the math of the microscopic and the physics of the massive. When a black hole only 11 miles wide begins to consume its neighbor, it creates a signature that resonates across every spectrum we can measure. We are learning to listen to the silent vibrations of space-time itself, using them to verify the internal mechanics of a disaster occurring 8 billion light-years away. In this new age of astronomy, the silence is just as informative as the light. If you were to step outside tonight and look toward the southern sky, your eyes might settle on the constellation Scutum, the Shield. It is a small, unassuming patch of the heavens, nestled within the crowded, shimmering dust lanes of our own Milky Way's galactic center. This region is a dense forest of stars, a chaotic neighborhood where the foreground of our own galaxy often masks the ancient secrets of the deep interior. Yet, it was through this thick veil of local stardust that the signal arrived, piercing through the heart of Scutum like a needle through silk. To find the source, astronomers had to look past the millions of nearby suns to find a single, massive galaxy, twice the size of our own, buried so deeply in its own dust that it nearly defied identification. This discovery was not the triumph of a single nation or a lone observer, but a testament to a true United Nations of astronomy. As the alert went out, the machinery of a planet began to turn in unison. In the high, thin air of Hawaii, the Gemini North Telescope swung its massive mirror to capture the fading optical afterglow. On the plains of New Mexico, the dishes of the Very Large Array pivoted to listen for the radio hiss of the expanding shockwave. Above the atmosphere, the Fermi satellite and the James Webb Space Telescope worked in a synchronized orbit, sharing data across the vacuum of space. It took a planet to understand a single star's death, a global realization that our small, fragile world is the only place in the local cosmos capable of mourning a sun 8 billion years gone. Now, we return our focus to the center of that storm, back to the 11-mile wide heart of the mystery that started it all. Even with our most advanced sensors, there is a limit to what the light can reveal about the moment of transition. We see the glow, we measure the heat, and we map the chemical signatures of the host galaxy. Yet the true nature of the final collapse remains a guarded secret of the singularity. It is a humbling reminder that even with our global network of guardians, we are still just children sitting on a shore, watching the waves of a distant, unseen ocean. Now, as the lights of our instruments dim, we find the ultimate meaning in the silence. The scientific instruments have given us the numbers, but to understand the soul of GRB 250702b, we must leave the cold data behind and travel across 8 billion years of light to the very edge of the event. Imagine a star that has already lost its outer identity, a massive helium sun stripped of its hydrogen veil by the relentless gravity of a nearby companion. It is a naked, burning core, spinning in a frantic orbital dance with a black hole only 11 miles wide. This was the stage for the stellar feast, a process that did not happen in an instant, but in a series of agonizing, beautiful layers. We finally understand that the ghost signal, those strange X-rays detected 24 hours before the main explosion, was the sound of the star beginning to break. It was not a sudden snap, but a structural surrender. The black hole's gravity was peeling the star's atmosphere away like silk, spiraling the stellar material into a glowing accretion disk that shrieked in X-ray light before the final plunge. This precursor was the star's silent warning, a testament to the fact that the longest flash in history was not an ending, but a violent, beautiful redistribution of everything a star was. As the final seconds approached, the black hole did not merely consume the star, it inhabited it. The singularity sank into the heart of its companion, and the resulting eruption was a 7-hour exhale of pure energy. This was the moment where 2.2 times 10 to the 54th power ergs of potential was converted into a kinetic legacy. While we see the light as a fleeting signal, the host galaxy feels it as a transformation. This energy is now a gardener, seeding the thick, dusty clouds of that massive galaxy with the heavy elements forged in the star's final moments. Gold, platinum, and uranium are scattered into the void, carried on a shockwave that travels at nearly the speed of light. In the vastness of the cosmos, we find a strange kind of peace in this destruction. The death of this stripped star is a prerequisite for the birth of something new. Those heavy elements, once trapped in the core of a dying giant, will eventually drift and cool, settling into the gravitational wells of future nebulae. Billions of years from now, in that distant and dusty corner of the universe, new suns will ignite, enriched by the ashes of the 7-hour flash. They will perhaps be circled by rocky worlds, planets made of the very iron that once spiraled into a 3-solar mass black hole. It is a nightly ritual for the universe to trade one form of existence for another, ensuring that no energy is ever truly lost. We are watching the celestial clockwork at its most extreme, seeing how a single catastrophic event provides the building blocks for an entire sector of a galaxy. The violet light of the burst has begun to fade now, transitioning into a warm golden glow that slowly dissipates into the background radiation of space. The fire has finally gone out, but the warmth of the knowledge remains. It is a lingering heat, a quiet resonance that suggests that even in the near-total absence of everything, the memory of a star survives in the light we were lucky enough to catch. As the violet-hued echoes of GRB250702b finally surrender to the velvet dark, we find ourselves returning from the edge of the observable horizon to the quiet sanctuary of the present moment. The data points have been collected, the spectra have been mapped, and the immense churning hunger of that distant black hole has finally been sated by the remnants of its companion star. 8 billion light-years of travel have culminated in a few hours of intense observation, a blink of an eye in the life of the cosmos, yet a transformative epoch for our understanding of how the universe's most violent fires are stoked. Now, as the instruments of the James Webb Space Telescope pivot toward their next target, we allow our own focus to soften, drifting away from the high-energy physics of the burst and back toward the steady, rhythmic pulse of our own world. The room around you is a place of absolute safety, a small pocket of order and warmth in a universe that is, for the most part, defined by a near-total absence of everything. While the light of that record-breaking flash was screaming across the intergalactic void, traversing the vast, lonely stretches of the cosmic web, the atoms that make up your bed, your windows, and the very air you breathe were part of a different, quieter story. There is a profound, bone-chilling cold in the spaces between galaxies, a vacuum so perfect it would break our brains to truly comprehend its emptiness. And yet, here you are, shielded by a thick atmosphere and the gentle pull of a planet that has remained a stable harbor for eons. The scale of the universe is a distance that breaks our brains, but it also serves as a reminder of the incredible rarity of the peace you are experiencing right now. Consider the journey that light took to reach our senses on July 2nd, 2025. When that star in the constellation of Scutum first began its collapse, when the black hole first began to peel away the layers of its helium companion, the Earth did not even exist. The sun was not yet a glimmer in a molecular cloud, and the iron in your blood was still scattered across the spiral arms of a younger Milky Way. That light traveled for 8 billion years, moving at nature's ultimate speed limit, passing through the births and deaths of entire generations of stars, just to arrive here. It is an old light, a patient light, and now that it has been seen and recorded, its long mission is over. It has found its rest in our archives, just as you are finding your rest in the silence of the night. We often think of the universe as a place of chaos and terrifying power, and in some ways, the 7-hour flash of GRB 250702b confirms this. We see black holes the size of cities swallowing suns, and we see gamma rays capable of sterilizing entire star systems. But beneath that surface-level violence, there is a mathematical elegance that should bring us a deep sense of comfort. The laws of physics do not change. They do not waver or grow tired. The same gravity that governed the micro-TDE in that distant, dusty galaxy is the same gravity that holds you gently against the Earth. The nuclear forces that powered that record-breaking burst are the same forces that keep the atoms in your body from drifting apart. Even as record-breaking bursts occur, the laws of physics remain a stable, comforting floor beneath our feet. The universe is predictable in its mechanics, even when it is surprising in its scale. If we were to look up tonight toward the constellation of Scutum, we would see nothing of this event with the naked eye. To our limited vision, the shield remains as it has always been, a soft, glowing patch of the Milky Way, crowded with the light of thousands of nearby stars. The galaxy that hosted the burst is hidden behind a wall of dust, invisible to all but our most sensitive infrared eyes. This constellation remains, indifferent and vast, a silent sentinel in the southern sky. It does not care that we have finally decoded its secret. It does not boast of the gargantuan energy it briefly channeled toward us. It simply exists, a collection of suns and shadows that provides a sense of celestial clockwork to our night. There is a strange kind of peace in that indifference, a realization that the universe is far too large to be bothered by our small human anxieties. We are, in many ways, still just making steam, trying to find more complex ways to understand the basic heat and light of creation. But through missions like the Einstein probe and the JWST, we are beginning to see how the sausage is made on a universal scale. We are learning that even the most extreme events follow a logical path, a sequence of cause and effect that we are smart enough to decode. We are the universe experiencing itself, a collection of stardust that has gained the ability to look back at its own origins. This realization is not a burden. It is a nightly ritual of gratitude. We are safe because we understand the limits of the dark, and we are home because we have mapped the fires that illuminate it. The journey of GRB 250702b has taught us that the universe is a place of grand fires and long silences. And tonight, you are safe in the silence. The high-energy photons have passed us by, continuing their expansion into the infinite, leaving behind only the data points that allow us to sleep with a little more clarity. The vacuum of space is not a threat. It is a backdrop for the incredible, unlikely warmth of our lives. As you settle deeper into your pillows, let the scale of the cosmos shrink back down to the size of your room. Let the 8 billion years of history fold into the simple, rhythmic breathing of the present. You are a warm data point in a cold void, a spark of consciousness in the eternal dark, and that is enough. The stars in Scutum will continue to burn, and the black hole at the center of that distant galaxy will continue its silent, dark rotation. But those are stories for another light cone. For now, your only task is to surrender to the gravity of sleep. The universe has shared one of its greatest secrets with us, and in doing so, it has reminded us that even the longest, most energetic flash eventually finds its resolution. The fire that wouldn't go out has finally faded into the background, leaving the sky clear and the night still. There is nothing left to solve, nothing left to observe, and nothing left to fear. The laws of physics are holding, the earth is turning, and the silence is absolute. Take a deep breath and feel the weight of your own existence, the stardust in your veins, the iron in your heart, and the quiet electricity of your thoughts. You are a part of the celestial clockwork, a vital and protected gear in a machine that spans billions of light years. The distance that breaks our brains is merely the measure of our home, and the light that traveled for aeons was simply coming back to where it belongs. As the final blurred stars of our visualization fade into a soft, total black, remember that the dark is not an empty place, but a resting place. It is the cradle from which all stars are born, and the sanctuary to which all light eventually returns. The records have been broken. The mystery of the 7-hour flash has been solved, and the instruments have been stowed. The universe is quiet now, its grandest fires reduced to the embers of memory and the soft glow of infrared light. You are tucked away in a corner of space that is peaceful and constant, a place where the only thing moving is the slow, steady drift toward dreams. Sleep now, as the light of 8 billion years ago finally finds its rest. Your journey through the light of GRB 250702b is complete, and the long drift into the silent dark has begun. Sleep well, tucked inside the shield of Scutum and the safety of the known. The universe is watching over its own, and all is as it should be.